one is starting to cool down. But notice for this one, that is not the case at all. The hot water was already at the top. The hot water wants to rise, and it'll stay there. So there is no convection going on here. The only way these are going to change their temperature is by conduction. This one is changing by both conduction and convection. And this one will actually become lukewarm very, very quickly. This one is going to stay hot for a long, long time. And that's that difference. And I'll say it again, just like conduction, we don't have any real equations to do for this class. We'll save the equations for later on in Physics 123. It's more about the conceptual idea and noting when and where and how significant convections can be compared to just conduction on its own. Well, I'm, again, talking and telling you too many, I think, good examples, but maybe you could figure those out on your own. I better get to the very last one of this, and that is the third way of transferring energy is referred to as radiation. And radiation is a little difficult to kind of explain here at this point in the semester. When we get to what we're going to call electromagnetic waves, it will make more sense. But maybe the best way I can explain it, and I'm glad your author has it, even though it's kind of hard to fully understand this one at this point, I'm glad he includes it because it's an important one too. And I think if he just did two of them, it might leave you with the impression that there's only two mechanisms of transferring energy. And there is not. There is these three. The conduction and the convection are the only two of these three that have to do with the material itself, the atoms. And so that's why they fit into this section about the structure of matter. Radiation I will try to explain to you, but I will do that in kind of a short window because like I said, it doesn't involve the structure of matter. It's an important one, but it doesn't involve the structure of matter, which is why, like I said, I'm glad he presents it here, but he doesn't really talk more about it until later on. And I'll do the same thing then. And I think the best way I can do this is to say the sun or any light bulb is a good example of something radiating. If I take the sun, you know already that light comes from the sun. What you may not know, and what we'll talk about here later, is that light fits into this category of electromagnetic radiation. And so I'm sure you know that standing in the sun, you will feel this warmth. You will feel this energy. This is the sun transferring its heat energy, which is 93 million miles away, to you. And so if you go stand in the sun and maybe on a cold day, you would enjoy it. You would go, and you were a little cold, and maybe you were in the shade, and you come out of the shade, or you're inside in a cold room, and you come out and you get into the sun and you feel that warmth. You feel those electromagnetic waves. Now I want to emphasize, electromagnetic waves are more than what the human eye can see. So they are more than light. But the easiest way, and I think the best way I can explain it at this point, is to refer to them as light, because that is energy. But what I also want to emphasize, and I'll emphasize it with this little picture, there's a wave. And as we'll talk about in the future, what is waving is an electric, and for that matter also a magnetic field. But I want to emphasize there are no atoms, there are no molecules. So this is the only process that can transfer energy in a vacuum, right? Both the conduction and the convections required atoms. That's why when I stand outside and get that sunlight, the 93 million miles between me and the sun, although maybe I should say the upper atmosphere and the sun is all a vacuum. There's no molecules out there. But can the energy from the sun get to me? And the answer is absolutely yes, it can. And it does it by only one way: electromagnetic radiation. And usually we don't think about something radiating this energy until it gets warm enough that we can feel it. So if we stand by a campfire, especially after the campfire is mostly out and there's just ashes or charcoal left there, the glowing coals, you can feel that. You put your hands on it and you go, oh yeah, I can feel something. That's what you're feeling. You're feeling this radiation. There's not much light to it, but there's a lot more radiation outside of the eye. We call that a thermal radiation. You can feel that. The sun has a lot of that too, but the sun also has a lot of visible. So the sun makes a good example because you can not only see the light and feel the light, but you can also feel the other parts of it, what we call the thermal radiation, the stuff that you can't see with your eyes, and it's enough that you can feel that warmth. And again, a campfire is just like that. Another really good example is a car after it's been driven. The radiator is really hot. And if you walk in front of the car, you will not see any light coming from the radiator. But if you stand near the car, especially if you put your hands out, you will feel that warmth. So the best thing I can say for this chapter here is that there is this third piece of how energy gets transferred. It's an electromagnetic radiation. And this then acts a lot like light. And so for you to understand it, I'm going to use the analogy of light. That's why, again, on a cold day, if I went outside and I wanted to get warm, should I be in a white t-shirt or a black t-shirt? Well, the white t-shirt is reflecting the sunlight. So if you want to keep the energy, you go with the black t-shirt. So if you want to stay warm outside, you put on a black t-shirt. And what about a hot day, a summer day, and I want to keep cool? Well, outside I'd put on a white t-shirt. But here's where it gets kind of interesting. That I think most people understand. But to show you thermal radiation, let me try this experiment. I think those will stay okay. Let's see what happens. Let me put some hot water in a reflective one. I don't have white, I have silver, shiny, and a black test tube. So here's my hot water. And I guess the first thing I'll do is kind of put a little hot water in each of them because they are at room temperature. This will kind of pre-warm them, if they will. Okay, let me pour out that water. So now I've got some warm tubes. And so let me put in some hot water that doesn't cool down so much because I've already warmed the tubes. Let me try to fill up the tubes to about the same amount, so they have the same amount of water in them. And then let me take some digital thermometers here, and let's look at their temperature as they cool down. And so this first one here will be the black one, and it's at 73 degrees Celsius. And then I'll do the silver one, which it is, of course, 73, roughly the same temperature. But I have a tough question for you. See if this makes sense. Which one will cool faster? The silver one or the black one? Maybe I'll call it white and black, like our t-shirts. Because again, if I went outside on a summer day and I wanted to stay cool, I would get in a white t-shirt. But what about it inside? You see, here's what I'm trying to show you. I'm trying to show you that not only does the sun radiate, but anything that has temperature radiates. My body radiates. So if I put on a shirt, I need to balance the radiation that is coming from the sun versus the radiation that's trying to leave my body. You see, if I'm outside with a white t-shirt on, the sunlight will hit me and bounce off, and that's good because I want to stay cool. But the radiation in my body will hit my white t-shirt, bounce back, and get trapped inside. That's not good. However, the sun has more thermal radiation than my body, so the fact that I reflect the sunlight is better than the fact that I reflect my own body radiation back into me. So that's great. But think about this if I'm in the house, if I'm inside. If I'm inside, it's a different answer. Because if I'm inside, I don't have the sunlight hitting me. All I have is the white t-shirt hitting me and reflecting my own body heat back into me. And so I actually am trapping, I'm actually reflecting that radiation back inside of me. And so on a white t-shirt on the inside, I will stay warm. So if I wanted to stay cool on the inside, I'm better off with the black t-shirt. See, because the black t-shirt would work like this. The black t-shirt would take the radiation from my body, and as it goes out and it hits the black t-shirt, it gets absorbed. And so the black t-shirt gets warm. It doesn't put it back to my body. And then hopefully my black t-shirt is kind of loose. And so the convection currents will flow out and take that heat out of the t-shirt and away from me. And so I can stay cooler on the inside in a black t-shirt. And I hope that's what you're seeing in this experiment. Which one cools faster? It might be a surprise. Look at this. The black one is down to 65.5. The shiny, reflecting one, the silver one, I'll call it the white one, is still at 70 degrees Celsius. Because this one reflects the heat back into itself. This one lets the heat hit the black on the outside and then takes advantage of the convection currents. And so I am cooling down quicker in a black object in the inside. I'm letting the heat out of my hot object. And that's a little difficult to understand. But I hope that made sense. And the best way to think about it is, again, just think about it in terms of light. It's why I really like these thermal flasks. These things are amazing. This thermal flask, if I open it up, oh, and I guess I've got my ice water in there, so I don't know if I can really show you the inside. But the inside is shiny. It's a shiny, reflective one. I have an old-fashioned thermos over here somewhere. Let me grab it. What did I do with that thermos? Oh, I think it's back under... Oh. Okay, I don't have an old-fashioned thermos. Thought I brought one. What I want you to then see is that the engineers did a brilliant design in this. The inside is silver. See, because what happens here, if I put a cold drink in here, then the radiation hits the silver and bounces back and keeps the inside cool. Or the other way around. If I put a hot drink in here, the radiation tries to get out, hits the shiny silver, and bounces back in. They even did something better. Oh, watch this. I'll have to draw a picture for you to see this. Oh, here's a thermos. I walked right by. But if I take apart the old-fashioned thermos, that is really what these are. Although these are a little better than this, as you'll see here in a second. But see how it's shiny? And it's shiny on the inside and shiny on the outside. It has a thickness to it. And that's what I wanted to draw up here. This thermos, or these thermal flasks, have an inside chamber where you put the drink. Then they have some thickness to it. And they make it really shiny, a silver, because the silver then kind of reflects it. Now, it's not necessarily real silver. It could just be aluminum atoms and polished, and so it looks nice and silvery. But that would reduce this radiation effect here. And so, like I said, it works both ways. You put a hot drink in here, and as it radiates out, it reflects it back in, keeping it hot. That's why a lot of those emergency blankets, I don't know if you've seen one. I keep one in the glove compartment in my car. I hope I don't ever need an emergency blanket. But it's not very thick, but it's a shiny silver. Because when you wrap yourself in that shiny silver blanket, and you know, your car breaks down up in the mountains and it's cold, you get that thing out of the glove box and you wrap it around you. Or you see the kind of a NASA space station and you know, something goes wrong and they're stuck in the cold environment. They wrap themselves in this shiny silver thing. It reflects it back into them, so it keeps it warm. It also works the other way. That heat on the outside reflects back and keeps it cold. And that's what I have today. I have ice water in there today so that it will stay cold. But the other neat thing here is, remember, there's three ways to transfer energy. There's conduction, convection, and radiation. And remember, those first two, conduction and convection, requires the atoms themselves. Now, the makers of this thermos fill the area in between with an insulating styrofoam. Styrofoam's really nice because, number one, it doesn't conduct very well. And then number two, it takes up space so that if there was any air in there, it couldn't circulate around with convections. So this styrofoam stuffed in here stops convections and significantly reduces conduction. But you know what would even work better? What if you put nothing in here, a vacuum? Right? Remember, to have conduction or convection, you have to have molecules. So the makers of these thermal flasks did even better. They made two chamber walls with a vacuum in between. That's why these all have a unique sound when they're empty. Mine's got in full, but if you bang it, and this doesn't have it, I should bring an empty one. But if you bang an empty one, you'll hear that inner chamber just kind of shake around. Because the inner chamber is not connected very much to the outer chamber. There's a huge vacuum, and this inner chamber can shake back and forth. And the reason they put a vacuum in there is because now with a vacuum you won't have any conduction or any convection. And then you reduce the radiation with the silver stuff. Now, you do have to connect it at the top to make a vacuum. So there is going to be a little conduction here. And there, of course, it's not perfect in terms of a vacuum, so you have a little bit of convection. And also the silver isn't a perfect reflector, so there is a little bit of radiation. And so it has very little conduction, very little radiation, very little conduction, convection, and radiation. And so this stays cold a long time. And so I will fill this up, and you probably have yours, and you fill it up with ice in the morning, and it still has ice by the end of the day. It's amazing. Or the other way around, on a cold day, I can fill it up with a hot coffee or a hot cocoa, and it will stay hot all day. And then, you know, the thermos, really the same way. Well, I've really out of time, but I've got to show you a couple more things here real quick to call it an end of the chapter and get you ready for the test. I couldn't resist then these thermal guns. I don't know if you're familiar with them, but they're going to be much more common with the pandemic as we're opening up. One of the things they're saying here is when you go into a crowded place, the government agency is required to check your temperature. And Ron was just telling me he had a gathering where as they would walk in, they checked his temperature. And the thermal guns are nice. I'll kind of show you. This one, there's a little red dot here on the board. And that little red dot is a little laser pointing out. That red dot doesn't record the temperature. That red dot just tells me where am I pointing it at. Because it's this opening right here that is trying to get the radiation to come in. And the little sensor and then the computer on here measures that radiation. And so it uses the thermal radiation to say what is its temperature here. So in this case, if I came over to here and I used it, let's say I use it on this piece of wood, I could then shine it onto this piece of wood. And then back here, it would tell me, after the computer analyzed what radiation is coming, what the temperature is. And so this is saying the temperature of that piece of wood is 23.4, which is a little warm for a room, but very reasonable. If I come over to here and I look at this hot water up here, and so I pull the trigger on it, it's saying that top piece is still 61 degrees. And I'm in Celsius. Yeah, Celsius. And so that top one is still warm. Or if I shine it down here at the bottom one, the bottom one is still cool. It's 23 degrees Celsius. Whereas this one, where I actually used the convection currents, the top one has cooled down to 40 degrees. And the bottom one has warmed up to 40, or in this case 41. This hot one over here, at least the outside, I thought I'd get a bigger number. It's 29. By the way, in passing, I'll point out, see again, notice the black one is much cooler than the silver one. Anyways, I'll just take my own temperature here. So I'll put it on my forehead and see what I get. 32.6, which is a little bit low for a forehead. Remember, your internal body temperature is 37. And so your skin temperature, your forehead's a little bit lower than this. So I'm at about 33. Usually I record about a 35. So I'm kind of, I guess that's a good sign. I don't have a fever. I guess I don't have coronavirus yet. So, okay, so I'm got the thermal radiation. But you start traveling around and going into stores and stuff, they're gonna, you're gonna see a lot of these thermal guns, I think, as they take our temperature. Now, one more thing as I wrap up. Your author kind of does a weird thing at the end, and I want to point out a number in this weird thing. Do you remember our discussion on thermal expansion? Remember I said that the difference between something hot and something cold is when it's hot, the molecules move faster. If they move faster, they bump a little bit harder. If they bump a little bit harder, they need more space. Do you remember then this experiment I had? Where'd it go? This metal rod. And I put this metal rod up here. And I put the metal rod on this needle. And I heated it up, and the needle expanded out. We talked about it conceptually, but we didn't give you any numbers. And for whatever reason, your author chooses to wait until this chapter to give you the calculations. And I'm not sure why he does that, but nonetheless he does. So I'm going to follow suit with that. And so as I wrap up this chapter, let me just go to thermal expansion and say that if I had a rod of length L, and if you remember when I did it, it was 1 meter long, and I heat it up, and so here I put a flame underneath it, it will get bigger by a distance of delta L. And maybe he puts it in this chapter to point out that this growth is different for the different materials. So just like we had a different specific heat for different materials, just like we have a different latent heat for different materials, we have what we call a coefficient of expansion. Coefficient of expansion. The coefficient of expansion is really a number that is saying how much does 1 meter of that material grow when you warm it up 1 degree. It would look like this. The symbol that we like to use for the coefficient of expansion is alpha. And so how much does it grow per meter? So delta L per L. That's what that would mean, right? The delta L is how much did it get bigger. The per meter means, of course, you got to talk about 1 meter. So in other words, if something grows 1 centimeter, but it's 1,000 meters long, the growth per meter, we got to take that 1 centimeter and divide it by 1,000 meters. And then, of course, per temperature change. And so every material has a different coefficient of expansion. I like to write it this way. I like to put delta L equals, and as I was saying earlier, partly because I prefer equations without fractions, but partly because this is how I would write it when I said this is how much it grows. This is total. And so how much it grows depends upon what is the material, how much did I warm it up, and of course, how long is it? Because together, each meter grows. And so if I like a bridge that's 1,000 meters long, made out of steel, the bridge comes up on a summer day, let's say Celsius, I put all that together, and that tells me how much the bridge would get bigger. The SR-71 we talked about, I would need to know that. The SR-71 is made out of titanium. So I would have to know, okay, what is the thermal expansion coefficient of titanium? How long is the SR-71? I think it's 108 feet on the tarmac. And then how much does it warm up? Well, it warms up a lot. And I put all those in, and I would get how much the airplane is going to warm up, or how much the bridge warms up. But I did want to say that your author doesn't give you a chart. And in the past, I've had students struggle on a homework problem because they need the number for, and I think it's concrete. Let me see here. No, it's steel, I think. Coefficient expands. We obtain the following relationship. And so somewhere in here, he says, here's the bridge. It's made out of steel. And he gives this number for steel. The expansion is 0.000011. Now the units are per degree Celsius. But I wanted just to make sure before I finished up this chapter, even though I know I've gone way over time, is to say you're going to need that number. And in the past, I've had a lot of students ask me about it. And since we're doing things remotely, I thought maybe I'd jump on that before you guys sent me a bunch of email. Because there's not a big table. I suppose you could Google it and look it up also. But he gives it to you buried in an example problem. And students often miss that one. So you will need that number. He does one more thing, and so I'll say this kind of quickly. He says, be careful with thermal expansion because you could get the wrong idea when you look at ice and water. Most people know that if you put a bottle of water in the fridge, once it freezes, it actually gets bigger. It doesn't get smaller. And so a lot of times when I tell students, hey, when things get hotter, they get bigger, and when they get colder, they get smaller because of the motion of the molecules, they look at me like I'm crazy. They say, no, I have put a plastic bottle in the freezer. And when it freezes, it comes out of the freezer, it has expanded, it has broken the bottle, and it's dripped water in the freezer, or it is just this big ice blob coming out in all directions. And so thermal expansion can get misunderstood because what I'm saying is when the molecules move faster, they bump harder, they need more space. That is thermal expansion. But what you're talking about in the freezer is you've actually changed phase. And so in addition to changing the speed of the molecules, you are also changing the way they are hooked together. Oh, let me show you. Remember what our model looks like for the liquid water? It looks like this. So if I start with a container that looks like this, and they're kind of warm and they're shaking, and I put this in the freezer, they will slow down. So they will get smaller because they slow down. But at the same time, they will start to hook together with spacing between them. And as they hook together, as they change phase, they're going to get bigger. So water, when you freeze it, is interesting because it gets smaller because it is getting colder, but it also gets bigger because it hooks together with a lattice structure and space in between them. And the bigger part, the change of state of the bigger part, actually makes the overall effect of ice bigger than the smallness or the shrinking due to the thermal stuff. And so that's why people confuse it. They go, no, my ice got bigger. And it's true. I'm not trying to say your ice doesn't get bigger. But what I am trying to say is there's two things going on in that freezer. It's getting smaller because of the motion. That's the thermal expansion and contraction I'm talking about. But it gets bigger because they hook together with some space. And your author has a little point about that, and also a point about nature, because what that would mean is something like this that gets smaller, gets bigger when it freezes, would be less dense. And you know from Archimedes' principle, if you put something with low density into a liquid, it would float. So ice does float in water. It does have a lower density. And if you didn't have that, the ice would have sunk. And of course, that would have been really interesting. Nature would have been very different had ice sunk, because then the cold air on top would have made the ice sink, and it would just keep sinking, and the whole lake would freeze, and the fish would die. But that's not what happens at a cold lake. The top freezes over and blocks the cold air from the rest of the lake, and underneath stays a liquid, and the fish live all winter underneath there before spring comes around and melts the ice again. And so the fact that it gets bigger is very, very interesting and very, very useful when it comes to nature. And he has a little section on that. So I thought I'd make that a little more clear. All right, well, I better stop now. We are into 13. Let me say it one more time. Even though we're behind, that's fine. I think I'm enjoying what I'm doing. I hope you are too. And so we will get started with 15 after the exam. But know this then, your job is to get working towards exam number 2. Chapter 7, Chapter 8, Chapter 11, Chapter 12, and now Chapter 13. So the test is 4 days away, 5 days. So don't panic, but if you haven't done anything yet, you got to get to work here. Test 2 is going to come quick, 11 o'clock. All right, I will see you Monday. Bye now.